Oh, okay. Okay. All right. Hi, everyone. So we proceed to our second topic. This is the second topic. We will focus on the sequential circuit. Sequential circuit design. So when we talk about sequential, okay, we will be dealing with CLK. We will be dealing with clock. Okay. So remember the task that we have in our lab 0. Okay, we also have clock in our multiplier design. Okay, so this is actually the example of a synchronous of a sequential design. Okay, multiplier with sequential design. Why we call it sequential? Okay, because we have a clock here. The clock signal ideally the shape of the clock is like this one. Okay, so the clock is used to synchronize the operation of the data. Okay, for example, in this case, we have input 0 and input 1. Okay, so let's say input 0 here. Okay, input 0. Okay, this is, let's say, 0, 1, the data, and this is 1, 0, for example. This is input 0. And then we have another input. Maybe I can type here. Make it bigger. Bigger. 1, okay. And here is so this. Okay. Okay. And here we have in zero. Need to input, and the other one we have clock. Okay. And then we can start drawing in for the input. So let's say this is the input number 2. Okay. Okay, the data is, for example, 1, 1. And here maybe 0, 1, for example. Okay. So when we have clock, so the clock, for example, in this case, positive edge means that on every rising edge of the clock, okay, the operation of the multiplication will happen. So for example, I use different. For example, during this time and during this time. Okay. So let's say during the first rising edge of the clock we call as T1 and the second T2. Okay. So during the T1, okay, the operation will happen. And then what about the answer? So the answer will remain until next rising edge of the clock. Okay, the answer will remain until next rising edge of the clock. So 1 multiplied with 3, okay, you get 3. So the answer 3 will become here. Okay, why not here? Because of the evaluation of the output, okay, on every rising or edge of the clock, like this one. Positive edge is rising lah. So during the rising edge of the clock, and then we get the answer. Okay, this is actually decimal 3 equal to 3. We get this value, and this value remain until the next clock cycle, which is until T2. Okay, So that's actually the purpose of having the clock, or what we call as sequential circuit or system. Okay, the sequential system will make sure that the data generated here, okay, or the data arriving here is ready, okay, for the operation until we get a stable output. In this case, 3 is a stable output for the other operation. Okay, you just imagine after, for example, this is your divider, your multiplier, for example. Okay, input number 1, input number 2, and your clock, for example. And the output of the multiplier goes to an adder, for example. This is your adder, for example. Okay, this is in number 0, in number 1. Okay, this is your clock. Okay, and then this is in number 2. Okay, in 2. This is in 0, in 1. Okay, clock, and in 2, and then you get the output here. Okay, this is we call as output. Out. Okay, this is what we call maybe out 0. Out 0, maybe this one out 1. Okay. Okay, here is out 0. Out 0. And then the data here that you get here, for example, you get the 3, okay. The value 3 will become the input to this one. Okay, to the adder. And then input 2, okay, maybe let's say the input is equal to 1, for example, the value equal to 1. So the 1 will, let's say the 1 a bit late, okay, a bit late. The 1 maybe somewhere here, maybe I need to read. Okay. Maybe 1 a bit late lah, somewhere here. Somewhere here. This is the unknown value, okay. You see the red color, or X lah, labeled as X in your simulation waveform. So, and then here is on the only value of 1, okay, for the input here. Okay, input here. Okay, so let's see the timing. So this is the second, the first. Okay, so just focus on these two. Okay, you see this is out 0 and this is in 2. Okay, this is in 2, and this is in 2, and this is out 0. Okay. So in this case, the input managed to arrive early, before the next rising edge of the clock. So means that your adder here managed to add these two values, and then you will get the value on the next rising edge, which is after second rising edge of the clock. So 3 plus 1 equal to 4. Okay, so means that you can see here, okay, this is actually the time that allow the data to do the operation. Okay, that's actually the advantage of sequential system with a clock. So the clock will do the synchronization of data. Okay, so this sometimes we call as token data token. We will see after this they call as token. Token that arrive late here and token that arrive early. So by the advantage of the synchronous or sequential design, okay, so the data will not catch up, and then the operation produce a reliable data at the output number 1. Okay, that's example of importance of a synchronous or sequential system. Okay, All right, so that's just an overview lah for the sequential system. Here we go back to our VLSI. This is actually to tell you about the challenges, okay, based on the previous lecture, okay, the industrial lecture that we have just now. We see that number of transistors getting more. Okay, so the greatest challenge is not designing individual transistor only, actually, but managing the system complexity. So that's actually the one of the challenges in modern VLSI, because the complexity getting higher, getting more, because we want a sophisticated chip to do sophisticated operation. For example, to do an AI algorithm on a smartphone, for example, on a computer, to do a deep learning process on a computer. So that requires a lot of algorithm, okay, a lot of sophisticated what we call architectures inside your design. Means that more transistor required. Okay, modern SoC design combine memories, okay, processors, IOs, okay, and dedicated application specific logic on a single chip. So this is actually the reality. So we have all integrated on a single chip. Okay, not only a processor. We need to have a memories, IOs, and also a specific logic. Okay. So the use of 100 of million or billion. So as we watch the lecture just now, so 5 billion. You just imagine 5 billion number of transistors. And the cost 10 of million of dollars and more to design. So the designing process will requires more. Okay. Right? The implementation must be divided and partitioned among large team of engineers. That's normal. Okay, we have a front-end engineer. Even front-end engineers also will be divided into several design engineers to do a complex design, especially. So when we talk about 5 billion transistors, then of course that's a very, very huge design, complicated design. Okay, we have also learned about the Y chart. Okay, so the more the complex, actually, we can see even the system is complex, but it's actually fundamentally comes from transistor, okay, transistors. So lots of transistors can create up to the more complicated system. Okay. All right. So we also have learned about this. Okay, just a revision. Okay. Remember, we have front end and also back end. Okay, so normally front end design we relate it to digital design, okay, whereby we have RTL or register transfer level design using VHDL, okay, or Verilog. Okay, these two are categorized under HDL, okay, HDL, hardware description language. And then we will synthesize it, okay, we will do logic synthesis to get an equivalent logic gate. Okay, though this is actually normally done using Synopsys DC or design compiler. So for those who have done your lab 0, you will see how the multiplier coded in Verilog HDL being transferred or synthesized to a standard logic gates. Okay, right. So before that, you also perform the behavioral or functional simulation, okay, to make sure that the written code function as expected. Okay, but that is actually not part of the implementation of a chip lah. Okay, that's actually a part of simulation only. Okay, so when we perform the logic synthesis, we will also do timing simulation, okay, power and optimization, okay, and also area optimization. Okay, so for this course, actually we'll focus more on the back end part of the design, okay, or simply we call it physical design. Okay, we will see on the placement or floor planning and placement, okay, and we will see the final placement and so on, okay, on the chip until we get the final chip before we go for the manufacturing process. Okay. We call it GDS. GDS. Here is actually the another representation of VLSI design overflow. You can see here behavioral representation. Okay. Logic representation, when we synthesize the HDL code. The behavioral representation, normally we use HDL, either Verilog or HDL, and then we synthesize it. Okay. And then we do the logic verification. We make sure that the synthesized logic, okay, already synthesized or not, completely synthesized or not. And that's why synthesizable behavioral design is very important. You need to write a coding with synthesizable code lah. Okay, some code are not able to be translated to equivalent hardware. That's what we call as non-synthesizable. Okay, when that design is non-synthesizable, in terms of logic synthesis, some of the logic gate might not be inferred, and that will cause a problem lah. Okay, okay, and that's why we need to do again verification. Okay, after functional verification, okay, at the behavioral representation, we also need to do logic verification to make sure that the functionality, for example, of a multiplier produce the same even after we do the synthesis. Okay, and then we will go into a very lower level, which is the circuit representation. Okay, and PMOS transistor, and then they have a standard cell that belong to that particular transistor, and then that develop the layout, okay, layout of the chip that we are intended to design. Okay, so that's what we call as physical design. And then again, we need to do another verification. So you can see the 3 steps of verification lah. Okay, behavioral or functional. Okay, we check during the first design stage, and then logic, and then the last one layout. So this is actually to make sure that our design is free from any errors. Okay, okay, before we do the fabrication. Okay, and then the step like the fabrication and testing. So DFT is here lah. The lecture that we have just now, talking about the DFT or DFX. Okay, after the chip we manufacture. Okay, all right. So physical design, okay, is very important, okay, and floor plan here is part of the physical design, okay, is the first step in the physical design. We call as floor plan. So why floor plan is very important? Okay, floor plan is used to estimate the block areas. Okay, you estimate lah. So just imagine this is your silicon wafer. Okay, your silicon wafer. Okay. And this is the die that will become your chip after you manufacture it, and then after you slice it. Okay. And then you want to estimate on one single die, okay, how many chip that you can occupy. Okay, how many die you can occupy. So that's normally we use a floor planning lah, to what we call to estimate the size of the die. Okay, the size of the die. So this is the die. Okay, this is normally the size of the normally in 12 inches lah, 12 inches, and your die is depends lah. Okay, smaller than that lah. Okay. Okay, so begin with block diagram. Normally we begin with block diagram, and each block diagram has input, output, and the function of it. Okay, and then we will see detail of the data path, array, and random logic inside it. Okay, to see it clearly, so you can have a look on our textbook as well. Okay, this is actually taken from your textbook. Okay, the CMOS VLSI design. Weste, so I type here CMOS VLSI. Okay. Weste. Page number, I think early page lah. Okay, if you found it, just let me know. Maybe we can share here. Okay, so Weste, right? So in this book, it explains detail about the chip floor planning. Okay, maybe I will explore it so that we can see Weste. Okay. Any question before we proceed? Okay. Okay, this is the textbook. Okay, just wait for a while to still loading. Okay. Okay. So here is actually the information. So physical design begin with a floor plan. So what is actually the function of floor plan? So this is actually the information. Maybe I can use the important words and paste that so that you can get the information. Okay. All right. So maybe I can here. So floor planning actually it estimates the area of major unit. So this is actually the definition. Okay, try to make it fit. Okay, so it estimates. Maybe not a good place to put a lot of words here. Okay, okay. Maybe I just make it smaller. Okay, so I just put here the definition. You can go into detail inside the textbook. Okay. Okay, here. Okay, the floor plan estimates the area of major unit in the chip and define their relative placement. Okay. Okay, for example here, okay, we have a die, okay, of size 1.5 by 1.5 millimeter. Okay, so this die, okay, 1.5 by 1.5 millimeter. And then given the system use 0.6 micrometer process, okay, and then from there you can estimate the size of the die in the unit of lambda. Okay, why people use lambda? Because lambda is a standardized unit lah, okay, so that people will know the size regardless of the dimension of the die. For example, in this case, in millimeter. Okay, so we refer one reference unit, which is lambda. So to get this one, okay, 5,000 lambda is actually you get from the calculation of the process technology. So 0.6 micrometer process, okay, is equivalent to estimation of 0.3. Okay, the lambda is equal to 0.3 size of lambda. Okay, 0.3 micrometer. Okay, 0.3 micrometer. How you get this? So this is actually based on the assumption that made inside the textbook as well. Okay, maybe I can find it for you. I think it's on link. Okay, before it. This is your textbook on page 51. Okay, page 51. It mentioned in here, okay, lambda is generally half of the minimum drawn transistor channel length. Okay, the length is actually the distance between the source and the drain of the transistor. So remember, transistor has a source and drain. Okay, so the length between that is they call as channel length. Okay, normally if given a process technology, for example, 180 nanometer process technology, okay, so you assume to 0.18 micrometer, and then to get the equivalent, what we call lambda value, they divided by 2. And that's why we get 0.09 micrometer. Okay, based on this assumption. Okay, lambda is generally half of the minimum drawn transistor channel length. Okay, to know detail, you go to page 51 of the textbook. Okay, and then from there, you divide 1.5 is actually equal to, maybe I can 1.5 equal to 1 can be small, make it bigger. So 1.5 millimeter equal to 1,500 micrometer. Okay, so to get the equivalent value in lambda, so you divide this by 0.3 micrometer. So if you hit your calculator, you will get it's equivalent to 5,000 lambda. Okay, that's why we see it equal to 5,000 lambda here. All right. So the 5,000 lambda, one side. Okay. So we can see here the other side also 5,000 lambda. Okay, one side and the other side. Okay, because it's 1.5 by 1.5. Now you get the dimension of the die that you plan to design your chip. Okay, so that's actually the estimation based on the floor planning process. Okay, so given also in the example, okay, in the textbook, this is also taken from the textbook, you can explore it further. Okay, they have 40 I/O pack. Okay, whereby you can see here we have 10 I/O, okay, on each of the side. Okay, and that's how they do the placement, okay, or the floor planning. So this is actually floor planning. This is the actual floor planning. You can see after doing the, I think this is after design compiler. Okay, synopsis design compiler. Okay, even in lab 0, you will see this design vision, design compiler, IC compiler. Okay, you will see this in lab 2. Okay, so and those on the corner, you can see here, those on the corner is actually reserved for power and ground. Power and ground. You see, that's how they do the placement or floor planning for a chip. Okay, and then in the middle they allocate all the logic lah. In this case, we have control logic and also data path logic. Okay, and then they do calculation the size of the net size lah. Okay, maximum possible core area, which is actually, this is actually the maximum possible core area after considering all the I/O port. So which is 3,500 by 3,500, and inside this core area they put the design, okay, the control and also the data path. Okay, detail of this you may refer to the textbook first, okay, and then we shall continue maybe tomorrow. Okay, we tomorrow at 9 o'clock we continue a bit before we start discussion on our lab. Okay, you can read this the textbook. Okay, the textbook. I think page on the floor planning just now. Okay. Introduction. Floor plan. Okay, inside here, and then go to page, this one. Page 73 or 46. Okay. Any question before we end? And then I will give you the attendance link. Any question?
No, doctor.
No, okay, I stop the recording first.